one of the most important topics we're going to talk about in this class is right here, the idea of a gradient. The gradient is actually a generalization of a derivative. If we think about a derivative being in a single dimension, then the gradient is a way to describe a derivative in a generalized way for multiple dimensions. Its usage spans very many disciplines. Pretty much anything that studies physical quantities and the change of those quantities uses the gradient. So it's hard to overemphasize how important this concept is. But luckily, if you understand the pieces that build up to this, its derivation, where it comes from, is entirely natural. So when we think about some function f, as long as the partial derivatives exist, then this idea of a gradient, which has this what we call a del operator. Think of like a delta but flipped upside down. Del of f, sometimes pronounced grad f or del f. You know, you'll hear those interchangeably used. It's a vector. So we've been dealing with a lot of functions that, you know, or a lot of things that generate vector functions or whatever. But this is the first time that we take a scalar function and we construct a vector out of it. So the thing that we generate is actually a vector with the partial derivatives in each direction being part of the I, j, or if I had three components, this would be partial with respect to xi, partial with respect to xj, partial with respect, or sorry, xi, yj, zk, and then so on and so forth. So you essentially say that the quantity going in that direction, take the partial with respect to that direction and assign it to that component in the direction. Again, very, very natural to think about this idea of a vector where the partials are along those axes. And what's cool about this is if we think about the directional derivative, well, the directional derivative is actually just the gradient dotted with the unit vector. Remember, in the directional derivative, it was the partial with respect to x times the first component of u, partial with respect to y times the second component of u. And then if you were to generalize that to more dimensions, it'd be the same idea. So by finding a gradient and then dotting it with this, we can arbitrarily describe directional derivatives using only information we know about the gradient. Again, it's a very, very important concept and quantity that spans so many disciplines. So we're only going to talk a little bit about it now. We're going to do some examples, but I don't want you to lose sight of the fact that this is a very, very important result.